So the title of my talk is an average John theorem. And you really need very little terminology in the beginning, and I wanted to just start with a really tiny amount of terminology, so we can discuss it. So, so we say that a metric space a space X with symmetric D embeds with by Lipschitz distortion. So I'll say with distortion, but so whenever I say with distortion, I mean by Lipschitz distortion, some parameter D into a normed space, call it maybe Y, with some space with some norm, if there is a D Lipschitz function f from X to the Banach space Y. So remember, D Lipschitz just means that fx minus fy is less than D times the distance from X to Y for any 2 points X and Y in the space. So if there exists a D Lipschitz function from X into Y, such that it doesn't contract distances. Fx minus fy is always at least the distance from X to Y in the original space. This is for all. Okay, so that is the notion of a by Lipschitz embedding or embedding with distortion D. And sometimes I will write this as X embeds with distortion D into Y. And this really means that we can faithfully represent X as a subset of Y. So we can associate to every point in X a point in Y. So if you take any 2 points in X and you measure their distances in the target Y, you get the right answer up to a factor D. Okay, so this is the notion of a by Lipschitz embedding. And really the starting point of this lecture is, so there is the following classical theorem, important theorem of Fritz-John. So 2 examples, 2 classical, the big theorems that started the field. Both of which will play a role in what we talk. So the first one is the theorem of John. This is 1948. It says that any n-dimensional normed space embeds with distortion root n into a Hilbert space. And that will be really the beginning of our talk, but and the other big major theorem of this fundamental theorem of the field is the theorem of Borgen from 1985, which says something analogous, but instead of about n-dimensional normed spaces, it says something about n-point metric spaces. So any metric space XD with X has endpoints, just an endpoint metric space embeds the same thing, embeds into a Hilbert space with distortion big O of log n, some constant, 10 times log n. Okay, so that's Borgen's theorem, but John's theorem is the starting point of my talk. It will connect to Borgen's theorem later, and we will see. Okay, so these are the two fundamental facts. I should have said then both are, this is sharp, cannot be improved, and this is sharp. So Borgen proved that this is sharp. So the fact that John's theorem is sharp is an easy fact. I will get to it later. The fact that Borgen's theorem is sharp requires some thought, and Borgen didn't succeed to prove that it is sharp in the time. He proved that there is an examples which require distortion at least log n over log log n, and it took 10 years to show that this is completely sharp. This was done by Lineal, London, Rabinovich. So in 1995, and we will get to that because that will be also very important for us. But the start is John's theorem, and the thing that many people, not only me, have been wondering about is, okay, every n-dimensional norm space embeds into a Hilbert space with distortion root n. That's a good theorem. It's a useful theorem. By the way, many of you probably know this theorem when the embedding is linear. So you approximate the unit ball of an n-dimensional norm space by an ellipsoid up to factor root n. This is the same theorem because there is a general principles, Rademacher's differentiation theorem, that if you find a Lipschitz embedding with a certain distortion, then there's also a linear embedding with that distortion. So this is really the same theorem. It's just equivalent to the same theorem, the way I stated it. But can we do better? So, right, the Lipschitz condition requires these bounds to hold for any 2 points in the metric space X. So if we relax that requirement and we just want them to hold for a typical pair of points or an average, can we do better than this sharp theorem, this root n theorem? This is distortion. Can we do better than the root n distortion? So the starting point is what I want to wonder about is in John's theorem, what happened? So I see it's changed to an eraser somehow. So in John's theorem, can we get better distortion if we only require this average guarantees? So we wanted this very stringent requirement. Every pair of points in the image have the right distance up to factor root n. We want this to hold an average. And the obvious objection to this question is, so obvious objection is what does average mean here? Remember the setting is X is an n-dimensional norm space. So it's really just Rn with some norm on it. And on Rn, there is no natural probability measure. So there is no canonical probability measure. On X, with respect to which the notion of average would make sense. So whenever we want to ask a question in mathematics, we want to make it natural. And in this case, there is nothing natural about the notion of average. And a standard mechanism to make in a setting like this, to turn a question into a natural question is to add the quantifier for every measure. Okay, so here is the proposition which makes this natural. So again, terminology. say that a metric space X embeds with average distortion D again, this is some parameter into, I'm really rewriting the definition from before into a norm space Y. Some Y with some norm. If, and here is how we make this natural, for any Borel probability measure. Mu on X, you give me your notion of what average means. Once you do that, then I will do the same thing, that there is a D-Lipschitz mapping f from X to Y such that, and now I'll just write the requirement that was before we wanted fx minus fy, their distances to be at least the distance from X to Y always. Let's make it be an average. Okay, so such that, so you look at the integral of fx minus fy squared d mu x d mu y. So you take two random points in your metric space, random according to the measure, which I didn't get to choose. This has to be at least the same thing in the original space as in the original space. Okay, and just one comment about the powers too. So this is it. Formally, I should be calling this quadratic average distortion. We could have taken the average distance, average distance to the power 4, right? Changing the powers will not change qualitatively any of the theorems that I'm going to show in what's coming. You can choose to change your powers as you wish. I focus on power 2 just to be concrete. So the average square distance, just to be concrete. Formally, I think in the paper I call it quadratic average distortion, and there is a p average distortion for the pth moment. And all of these things are understood and written, but let's just, for concreteness, call this the notion of average distortion, just for the purpose of this talk. Okay, just so is the concept clear? What maybe I have it before. The notion of distortion before wanted the function to be D Lipschitz and to satisfy this requirement always. And we are asking, can we do any better? In John's theorem, if we want it to hold only an average, and the new twist is that in order, the notion of average has the quantifier every possible notion of average on the space X, because this is just Rn, there is no canonical probability measure.
Can I ask a question?
Absolutely.
I'm a bit confused about the order. So you first pick your mu,
yes,
and then you pick an f, because of course I could pick from you something that has 2 point masses.
Yes. So if you choose your f to work for all mu, it's the previous notion. It comes back to by Lipschitz. If there were one f that worked for every measure mu, then you didn't change the notion.
Okay, yeah, right.
Because
okay.
f can be the two. Okay.
I see. Yeah, thanks.
Then you really didn't do anything. But your f depends on mu. Okay. Somebody chooses the notion of average. Now you get to choose your embedding. Yeah, it's a very good question, because that's the nuance here. We cannot flip the quantifiers because we don't change anything when we do that. It's the old situation. Is that clear? Okay.
Yeah, it is. Thank you.
Can I also ask a question, please?
Yes.
Yes. What happens if you, instead of using a product measure, you put a distribution on the pairs X, Y? Then
again, you don't change the notion. Okay, but by duality. Okay, but there are other questions you can ask. What about changing it in the upper bound? Right, we're still assuming the function is Lipschitz, and you can do that. in the theorems I'm going to prove for you, I'm going to get a D-Lipschitz mapping. So the upper bound I get for every pair. So it's just a stronger statement, but you could conceivably play more with this. Okay, but we're going to get Lipschitz map functions, and this is also natural for the applications I'm going to show. So yeah, there's flexibility, but this is the notion that I'm proposing. Okay. So okay, I'm proposing it, but this was known for a long time. So this is really due to Enflo in the 1960s. So everybody knew this, that with this notion of average distortion, there is no better John theorem. There is no better distortion. So by that I mean, maybe just the constants. So John's theorem said that every n-dimensional norm space embeds with by Lipschitz distortion into a Hilbert space, and the distortion is root n. And I can give you, Enflo knows how to give you, and we'll see that in a bit later, examples of n-dimensional norm spaces that don't embed even an average into a Hilbert space with distortion better than root n. Maybe the constant in front of the root n can be improved. Maybe it's not now. Maybe now it's a half root n that I never thought about. But in terms of the main asymptotic behavior, changing it to average doesn't do anything for us. Okay, so this is something that we knew all along, and therefore there was no hope to even. It was silly to think about an average John theorem, and you should be asking me, why am I wasting your time? And so here is really the main idea, in my opinion. There is going to be a proof at some point, but the main idea is just the following. I don't know, additional degree of freedom, doing an additional degree of freedom into the question. So this is hopeless. We cannot do anything better with average distortion. And the new idea is, and this is going to be a definition, is to use Helder mappings. Consider less regular, consider Helder regularity. So what do I mean by that? So again, terminology. So give me some number omega between 0 and 1, and then the omega snowflake of a metric space XD is the metric space XD, but you raise the metric to the power omega. So let's say if omega is a half, look at the metric space, the same set, but the new distance function is square root of the original distance function, or whatever omega is. Raise that distance to that power. So that's called the omega snowflake, because if you do this to the real line, so if you take the real line to the power a half, you get the von Koch snowflake. Okay, so, but this is something that you can do to any metric space. Little exercise, if you've never seen it before, just check that a metric raised to a power less than 1 is still a metric. It's still a metric space, X with the metric d to the omega. Okay? So that's a notion of an omega snowflake. Omega snowflake, what is a Lipschitz function from the omega snowflake of X into Y? It's nothing more than a omega Helder function, right? This is by design, that's what it is. A Lipschitz function with respect to the snowflake is a Helder function, omega, whatever the parameter is, with respect to the original metric. Just write what the Lipschitz condition means. The distance from fx to fy has to be no less than the distance from x to y to the power omega, because that's the notion of the distance, the new notion of distance. Okay, so this is the snowflake of a metric space, standard terminology. But this is a brutal operation to a metric space where the real line becomes something like a fractal, like the von Koch snowflake. This is something which definitely leaves the realm of John's theorem. Okay, so John really was looking at linear mappings, linear embeddings, and because by Rademacher's differentiation theorem, by Lipschitz mapping, any distortion that you can do with the by Lipschitz mapping, you can also do with the linear mapping. But Helder mappings are very nonlinear. A linear mapping is automatically Lipschitz. It will never be Helder. Okay, so I'm going to throw into the mix this snowflake, and here is the theorem. This is what I call the average John theorem. So I'm changing the rules of the game by allowing embeddings of snowflakes, and the theorem is that the 1/2 snowflake of any n-dimensional norm space embeds into a Hilbert space with average distortion so no, it's an average in the sense that I said big O, not of root n, but of root of log of n. Okay, so John's theorem said the initial metric, so Lipschitz mappings, not Helder mappings, can be embedded into a Hilbert space with distortion root n. This is the best you can do. I just showed you that, I told you, but we'll see, that an average, this doesn't help. If you want to embed the initial metric, you still need to pay a distortion of root n. But on 1/2 snowflake, the root n becomes root of logarithm of n. And that the fact that it became logarithm, that a power type is going to be crucial for an application that I'm going to show. Okay, so that's the new theorem, what I call average John. And I want to say some things. So I want to show you an application and I'll say maybe a few words about the proof, or there are several applications, but I'll work out one of them at least.
One question.
Yes.
What would be the best distortion, worst case distortion, not average distortion you could get with the same half snowflake statement?
Oh, I will get to that. Yeah, that's the comments I want to say next. So I'm going to say some comments on the theorem first. I'm going to answer that question in the next minute. Okay. So remarks. So I want to say, so this theorem is sharp, but it is what kind of an enjoyable for me. This is triply sharp. Never happened to me before. It means everything, and that's related to the question that was just asked. Every word in the theorem, there are three conditions which are new here. And if you remove any one of them, the theorem becomes false. So what are the three things? There is the snowflake, and I'll get to this. There is the notion of average. And, well, there is a number here. There's an asymptotic, a root log n. That I said the distortion, the average distortion behaved like a constant, like times root log n. All the things that are underlined, if you remove any one of them and keep the other two, the theorem becomes false. Okay, so what do I mean by this? So triply sharp. So first of all, the big O of root log n cannot be improved. We'll get to this. That means there exists an n-dimensional norm space such that if you want to embed its 1/2 snowflake into a Hilbert space with average distortion capital D, D must be at least a constant multiple of root log n. So you cannot do better than what we achieved here. So this is the first thing. The second thing is a 1/2 the Helder regularity. The Helder regularity cannot be improved. while getting average distortion. Logarithmic, with logarithmic behavior, which is going to be important for us. So what do I mean by that? I mean, the statement is, so there is a norm space. There is an n-dimensional norm space. Such that if it's 1/2 plus epsilon. So you want a little bit more, not 1/2 snowflake, but less brutal snowflaking, let's say 2/3 snowflake. You want to be closer to the original distance. The power is closer to 1. So if it's 1/2 plus epsilon snowflake, embeds with average distortion D into a Hilbert space, then D is at least n to the epsilon. Okay, so it's so if you want 1/2 plus 0.01, then the distortion that you're going to get is a power of n, not a power of log n anymore. Okay, so you cannot get more. So you cannot get better than root log n in the distortion itself. If you want more regularity of the function, I told you before you cannot get Lipschitz, but you cannot do better than 1/2 plus epsilon. Okay, and this is really just looking at n-flow's example, which is just L1 of dimension n, and the measure, you need to decide what to measure on it, is just the uniform measure and the vertices of the Hamming cube. So you just analyze n-flow's proof, and this is what you get. Okay, so, and then I said it's triply, and now I'll answer the question that was asked a moment ago. So the theorem, so we need average guarantee. So, right, the question that was asked before, let me just explain the nuance. I changed the rules of the game on you, right? I said, I'm not trying to embed the metric space itself anymore. Now I'm trying to embed its snowflake into a Hilbert space. And I said that everybody knew since the 60s that you cannot get average distortion everybody knew that John's theorem was sharp. You cannot do better than root n if you want by Lipschitz mappings. But maybe if you want to embed the snowflake of the norm, you can get a by Lipschitz embedding of the snowflake, which is the by Helder embedding of the original norm. So that requires proof that wasn't known before. But what do I mean by that? I mean that so if the omega snowflake of some n-dimensional norm space, but I know which one, of L infinity n, Rn with the L infinity norm, embeds into a Hilbert space. With, by Lipschitz, the old notion of distortion. D, then D is at least, well, there is some constant. So at least n to whatever the snowflake was, so omega over 2. But it's a power of n for every possible. So if you want 0.001 snowflake, it's still going to be a power of n. So that's what I mean by the theorem is triply sharp. I did change the rules in the game. I knew that was the question. I'm all of a sudden allowing Helder mappings, but Helder mappings still don't work in the by Lipschitz world. If you want to get logarithmic behavior, you need average, and you cannot do better than the root log. Okay, but you do go down from root n to root log n. So I want to show one application of this, which has a long history. But before that, I just want to say that, so relating this Helder regularity thing, with more geometry. So if I add some geometric assumptions on the initial norm space X, X is not written in the statement. If you're given a norm space X, if I don't write if I'm not interested in a general norm space, but I'm allowing some geometric assumption on it, and I'll tell you what it is, then I do know how to get better regularity. Okay, so, and that's useful for certain things. So I just want to say that a higher regularity is possible if the initial norm space is p-smooth. I want to say a few words about this because that's important. And then I'm going to show an application. So what is p-smooth? Because many people are more naturally, I guess, more familiar with uniform convexity, I'll explain it in the dual. But this is so uniform. I want to recall what is uniform convexity. So you have a norm space X, and you draw its unit ball. So this is the unit ball. It's the unit ball. So this is all the points X in X of norm at most 1. So what does convexity mean? It means that if you give me 2 points X and Y on the boundary of this unit ball, this is 0. And you look at their midpoint, then their midpoint lies inside. This just means that I drew a convex shape. The midpoint of X and Y lies inside the picture. Uniform convexity says that it lies inside the picture by a definite amount if the distance from X to Y is at least some definite number, right? So if you call this distance epsilon, then you want this distance, the norm of X plus Y over 2, to be at most 1 minus some delta of epsilon. Sorry, this is the distance, sorry, the gap. I'll erase. The way I drew it was correct initially. This is at least some delta of epsilon, which is some positive number, but the uniform in uniform convexity refers to the fact that the delta, how much X and Y are distance epsilon apart, the amount X plus Y over 2, this is X plus Y over 2. The amount X plus Y over 2 is within the ball is at least some delta of epsilon, which doesn't depend on X and Y. That's what the word uniform refers to. That's the obvious definition of uniform convexity. So for example, in Hilbert space, this is just a parallelogram identity. It says that the delta of epsilon is at least some constant times epsilon squared. You can check classical Euclidean geometry. And there is a deep theorem, a major theorem, an important theorem of Pizier. It happened. So Pizier from 75 says that if X is uniformly convex, then then it has an equivalent norm. Norm with delta of epsilon, at least some constant. It's always at least a power of epsilon. So a priori, when I say X plus Y is inside the unit ball by some definite amount, the definite amount can be some function of epsilon, but a tiny function of epsilon. It's like 1 over e to the e to the e to the 1 over epsilon. And Pizier says no. Once you know there is a definite definite lower bound which doesn't depend on X and Y in the triangle inequality, in the convexity condition, then you can pass to an equivalent norm. You can change this shape by a universal constant and get a behavior like in a Hilbert space, but instead of power 2, some power q, some positive power q. Q is some constant. has to be at least 2, but that doesn't matter. So that's why so uniform convexity comes with power type behavior automatically. That's what PZF proved. So here is the theorem that, so if you know, so if X is an n-dimensional norm space, with such that the dual of X, okay, the norm, the dual norm, is a Q uniformly convex. I didn't say what I mean. When I say this, when this happens, I mean, so when any 2 points you're inside by at least C epsilon to the Q, when the web, then that's what I call Q uniformly convex. Okay. So if the dual is Q uniformly convex, saying that the dual is uniformly convex is what in Banach space theory we say that the original space is P uniformly smooth when P is a conjugate exponent of Q, 1 over P plus 1 over Q equals 1. So if the dual is Q uniformly convex, then it's P over 2 snowflake. 1 over P plus 1 over Q is 1. Embeds into a Hilbert space with average distortion. Again, big O of root log n. But in this big O now it's the constant, I guess, this delta, the modulus of X star. It depends on the assumption, of course, the uniform convexity assumption, okay, of the dual. So notice that if P equals 1 is trivial, I should have said that. That's like means that the dual, it means the dual of 1 is infinity, and it means you get no lower bound. But P is bigger than 1 if you have like an LP space. So LP, when P is between 1 and 2, is P, its dual is P uniformly, is exactly Q uniformly convex. Then you get better regularity. And again, P over 2 is the best possible. Okay, so in many situations we don't have a general norm. The unit ball is not just convex, but there is the dual is, but it's uniformly convex. Then we get more regularity, but then we know exactly how much regularity we can get. Okay, and it's still we have this logarithmic behavior. So these were the statements. I want to pass to an application, but maybe it's a good time to ask: are there any questions about the statements?
Assaf?
Yeah.
I was just curious. So if you like have a stronger assumption, or if you go for like the W snowflake for W less than a half, can you also improve this distortion bound?
That's another. Yeah, for less than a half, it's also. I don't know the correct power of the log in that case, but it's still a power of a log.
I still log rate.
So this phenomenon of something changes at 1/2, and a power in n behavior becomes a power of log behavior persists below 1/2. Okay. But somehow it's true, but this is kind of a natural for me because I want to get more regularity, also not less. But you're right. Okay, it's still possible. It's still true. It would be strange if somehow a worse mapping would require higher distortion or something like that. So, but the strange thing doesn't happen, so we're fine. Okay. So let me give an application. So let me first work out the application and let me analyze a specific case, and then I'll tell you what the history of this is. And this application was actually something that led to also to algorithmic applications eventually. So now let me pass to finite graphs. So, I'm interested in embeddings of expanders. So let's G be a connected graph. And I'll always denote by D sub G is, so it's is the shortest path metric. Okay, that's a D sub G. Whenever I write D sub G in what follows, I really mean, I just mean the shortest path metric on a graph. And let's suppose that the vertices of there are n vertices. And let's suppose suppose that it is big O of 1 regular. So let's say 4 regular. So every vertex has 4 neighbors. In the graph, n vertices, and every vertex has 4 neighbors. And we wanted to have a spectral gap. So let A be the transition matrix, A sub G, I guess, the transition matrix of the standard random walk, the standard on G. So you start, so at every vertex, it has 4 neighbors, and you go to one of these neighbors with probability a quarter. So this is just, it's a matrix which has, so if the vertices, if V are the numbers 1 to n, if you want, then Aij is going to be a quarter if Ij is an edge, 0 otherwise. And that's the standard random walk. So right, it's a random walk matrix. So its eigenvalues are, I'll denote by lambda 1 in decreasing variance. So the biggest eigenvalue of a random of a stochastic matrix is 1. The next one is lambda 2 G to lambda ng. And so suppose that G is an expander, and by that I mean that 1 over 1 minus lambda 2 of G is big O of 1. It's a really right. So we're going to be taking soon a sequence of graphs, and they're going to be going to infinity, and we just want that the second eigenvalue doesn't approach 1 as the size of the graph goes to infinity. So that's what I mean by an expander. And now let's try to, and this is something that has been studied for a long time, and I will explain the history after proving the conclusion. Okay, so I'm reversing this. So suppose that this graph, so its vertices with the metric, the shortest path metric, embeds with by Lipschitz distortion. Then I don't need to say it, but I'm saying it, distortion. D some parameter into a finite dimensional norm space. Call it X. X, some norm with some norm. So suppose this happens. So let's write it. So we can find the mapping F from V into our norm space X such that for all X, Y, 2 vertices in the graph, if I look at the image between Fx, the distance in the image between Fx and Fy, that's at least the distance in the graph from X to Y and at most d times the distance in the graph x to y. So let's assume this, and I want to get some restriction in this situation. So why is this happening? Okay. So I want to use the theorem. So let mu be the uniform measure, so uniform probability measure on f of v. So this is an endpoint subset of x. The average John theorem was about an arbitrary measure on a finite dimensional norm space and we got an embedding of that with that notion of average. So I'm going to apply the average John theorem to the uniform measure and the image of the vertices of the expander, which are just some collection of endpoints in X, perfectly legitimate probability measure. So by the average John theorem, there is an embedding G from X into a Hilbert space. H is a Hilbert space. So now let's write what it means, right? We know that the distance between G of U and G of V in the Hilbert space is at most some C root log n, right? That was the distortion that I wanted. That was the Lipschitz constant times the distance in X between U and V. But it was the 1/2 snowflake of X. That was very important. The mapping was 1/2 Helder. Okay, that was the point. So that was, and okay, now we want the average with respect to the measure mu. Mu is just the uniform measure on f of v. So it's what I have here is 1/n², sum x and y vertices of my graph, and now you have g of f of x minus g of f of y. This is in the Hilbert space. Squared is at least the average with respect to the measure of what? Of the initial distance in x. I'm embedding x. I'm not, right? So I look at f of x minus f of y. So now remember, what does the lower bound have to be? I'm unraveling the statement of the theorem. It has to be the squared distance of the 1/2 snowflake. So I was embedding the 1/2 snowflake of x. It's important I'm snowflaking. So I took the distance in x. What is the square of the 1/2 snowflake? It's just power 1. So this power 1 is like 1/2 times 2. Okay, I'll erase this. Okay, so does everybody, this is very important. I'm using the theorem. So is anybody not convinced that I simply quoted the theorem correctly? This is an application of the theorem to the measure mu, which is the uniform measure on f of v, of capital V, the images of the vertices. This is, okay. Great. So here is if you want, the metric interpretation. So metric interpretation of spectral gap. This is what's called the we're still in this world of Hilbert space. I think the first person who used this systematically or said this is Gromov, but this is just linear algebra. It says the following, that for every vectors v1 up to vn vectors in a Hilbert space, if you look at the average sum, okay, again, so I'm thinking of this vertex set as the numbers 1 to n. rather than just our point. So the sum over the average of Vi minus Vj squared is less than 1 over 1 minus lambda 2. And then, okay, the average over edges. Ij happen to form an edge. Vi minus Vj. So the smallest constant that you can put in this inequality is just equal to 1 over 1 minus lambda 2. And this is really, I'm not joking when I say this is an exercise in the definition. This is just linear algebra. Expand the squares and just see what's written. And you see that this is the definition of 1 minus lambda 2, the Rayleigh quotient formulation of what a spectral gap is. So this is really just an interpretation of what spectral gap means. But let's use this. So here I have an average of square distances in a Hilbert space. Some vectors. The vectors happen to be whatever the mapping G from the average John theorem was. G applied to the points, which was the original vectors, which were the images of the vertices of the expanders. But never mind, these are G of f of x as x ranges over the vertex at V is a collection of vectors in Hilbert space, right? So we know that 1 over n squared sum, and what was it? It was G of f of x minus G of f of y in the Hilbert space squared. We know that this is less than 1 minus lambda 2 of G times the average of the same points. G of f of x minus G of f of y in H squared. But now let's remember, there was what did we know? What did we know? We knew that G of u minus G of v, G was 1/2 Helder with constant root log n. Okay, and we also knew that lambda 2 was bounded away from 1. So if we put this together, we get here that this is less than, we have distances squared here, right? So, so we have log n times the average over edges. Sorry, this is some average over xy, which are an edge. That was the whole point. And now we have fx minus fy in the original space x. It's supposed to be the 1/2 snowflake distance, but raised to the power 2, so power is 1. Okay. But what did we know about f? What we assumed about f, I should have kept it here, is that it's d Lipschitz. So let's write this information. So each term here is at most d times what? Times the distance in the graph between x and y, which, well, this thing is 1. So the whole thing is d. X and y are, this is sum only over edges in the graph. So all in all, we got that d times log n. Sorry, not log n. This was, nobody stopped me, right? N was a number of vertices. X was just an n-dimensional normal space. So this is log the dimension of x. We don't know yet what the dimension of x is. The average John theorem, which I asked, am I using it correctly? I did use it incorrectly in the end. You know, the root log, it's my fault for using n twice. N is not the dimension of the space like it was in the theorem. It was the number of vertices in the graph. It's completely, I'm sorry, but okay. So, okay, so log the dimension of x in here and here. Okay, sorry, I really did use it incorrectly. That's the upper bound. Now, but what can we say about this sum in the lower bound? Well, that's already given to us. That's at least the average in the original of fx minus fy, and fx minus fy here is at least the distance in the graph between x and y. So if you put this together, we get all in all that d log the dimension of x is at least up to constants, the average over some xy vertices, the distance in the graph from x to y. That was just the assumption. This is just the lower bound. It's, well, the whole thing here. That is, this is a correct application of the theorem. Okay. Now, the graph was 4 regular or bounded degree. So the number of vertices at distance r from a given vertex is at most 4 to the r. So if r is less than, let's say, log n over 10, then that's a tiny, tiny, tiny fraction of the graph. So that means every vertex, more than half of the graph is distance constant times log n away from it in the graph metric. That's just because of 4 regularity. That has nothing to do with expansion. So this is more than an average. For every point, more than half of the graph is distance at least, let's say 1 over 10 log n away from it, or some constant. So this whole thing here is at least log n. And here is the correct, this is n is really the number of vertices. So this is just a standard combinatoric counting. There can't, because every vertex has 4 neighbors, how many points can be a distance 100 from it? At most 4 to the 100. Okay. So if you go distance log n over 100, then that's at most n to the 1 over 10 or something. Then that's a tiny fraction of the graph. More than half of the graph is out of that ball. Okay, so now we can solve this, and we get that the dimension of x is at least n to some constant that was in this twiddle sign over the distortion. So let's remember, oh, I'm over time. Can I take 2 more minutes? Okay, so I assumed that this graph, this expander graph, a typical graph, a random graph has this property embedded into some normed space with error, let's say capital D is 100. And the conclusion was, oh, that means that this ambient dimension of this continuous object is actually huge. These are endpoints that somehow force the dimension of the ambient dimension to be at least some power of n. I'm giving you information about endpoints lying down in the target, x, that they are like the distance, their distances between them are like the distances in an expander. And using the average John theorem for the measure which I had no control on a priori, right? It was the uniform measure and the image of, and the vectors which happen to be the image of the embedings of the vertices. Using the average John theorem for that measure, and that we really needed the logarithmic behavior, we got that the dimension is big. Okay, so the mere fact that such a thing exists, not only that spectral gap forces the ambient dimension to be big, was open for a long time, and there is a history about it. Let me very quickly, I'll just mention the history and I'll stop. So this was a major question in metric embeddings in the area of dimension reductions for a long time. So Johnson and Lindenstrauss in 82 asked if any n-dimensional n-point metric space embeds into some norm space of dimension space called X of dimension big O of log. Embeds, when I say embeds, I mean with distortion by some universal constant, okay, 10 or. Now, why did they care about this? First of all, there is many reasons this would be natural if this were true. But this is clearly something that we would want. It would be if you have a general endpoint metric space, let's say an endpoint graph, the internet or whatever. If you could putting it in a low dimensional norm space is just finding a small number of coordinates, right? So in this case, log n, if it's a k-dimensional norm space X, it's k coordinates, such that in the image, when you measure the distance between any 2 points, you get the correct answer up to a constant. But there's only log n coordinates. In a norm, the distance between any 2 points is just the length of the length in the norm of the straight line joining them. So if the initial space was a complicated graph, this is a major simplification of the metric using only log n coordinates. So that this is something that if it were true, we want it to be true. In the very same paper where they ask is, they prove that this is true if your metric space was a subset of a Hilbert space. That's the famous Johnson-Lindstrauss lemma. So it is true that any endpoint subset of a Hilbert space embeds into a Hilbert space of dimension log n. And so they ask, what about the general endpoint metric space? Can we cook up a norm which is allowed to depend on the initial metric, but it has only log n coordinates, such that we can realize this endpoint metric space using log n coordinates? They had other reasons. They were interested actually in John's theorem, and they thought that this would imply, using John's theorem, that any endpoint metric space embeds with distortion root log n, because I mean, if x is dimension log n, then it embeds into a Hilbert space with distortion root to the dimension. So it's root log n into a Hilbert space. So they thought that would be the analog of John's theorem for metric spaces. And Borgen, when he proved his Borgen embedding theorem, which that's when I started with them, he proved a very, very fundamental theorem using a very fundamental method that he introduced. But he also disproved, so Borgen, and this is really what that was, he discussed this a lot in his paper, in 1985, disproved the Johnson initial question by showing that sometimes the dimension of x, he did it for a random graph, must be at least log n over log n. And there is some constant here. Okay, so sorry, log n over log n, that's that interesting square. Okay, so so you can, there are endpoint metric spaces such that if you want to embed them into a k-dimensional normed space X, k must be at least not log n. You can get log n, but you need something like log n over log n squared, which is asymptotically bigger than log n. But it's still really, really good. It's a small number of coordinates. Okay, so of course, and Borgen asked, what is the truth? What is the dimension that you can do? And in the decade that passed, I'm going to skip some references along the middle, but you should say that lineal.
May I ask you to keep a bit an eye on the time?
What?
May I ask you to keep an eye on the time because we're getting over time?
Yes, yeah, okay. So Rabinovich, I really am at the end. In 1995, proved the lower bound of log n squared. They improved Borgen's theorem by this log. Okay. And that was the best known thing until a major theorem of Matuszek in 1996, so roughly a decade after Johnson and Borgen did his work, proved that no, in a bad way, there are endpoint metric spaces such that if they embed with distortion big O of 1 into x, then the dimension of x is what we proved is at least n to some constant. I did big O of 1, so I even said the correct dependence on the constant, but that's a nuance. So at least n to some constant, universal constant. Okay. So this was a great theorem. I think this was in his citation of the European Prize. This was the first line, or one of the first lines. He brought in methods from algebraic geometry to prove it's an existential statement. And what I just showed you using the average John theorem is that any expander has this property. So it's not just an existential statement, but we know any graph with just having a spectral gap means that you do not embed into any low dimensional space. So there is no dimension reduction for expanders, and that the fact that you isolated what are the high dimensional metrics ended up being a very useful thing also in other places. But this is what I showed you now is an analytic proof that has nothing to do with the algebraic geometry, and it's a different solution of this question of Johnson-Linestrauss and Borgen, etc. Okay, sorry that I'm over time, and I'll stop here.